And last week we talked about the sort of the origins of electronic music synthesis in analog techniques, oscillators and filters, so-called subtractive synthesis. And they were, driven by practical considerations, that it was something you could do with a relatively small amount of circuitry that would still give you an interesting sound. But they were clearly synthetic sounds. They were sounds that were novel, but if you wanted to make something which sounded a lot like a real world instrument, a real world sound, it was pretty hard with those techniques. So now we're going to talk about some techniques that are more along those lines, where you can actually take real world sounds and reproduce them with high accuracy, but also in a way that allows you to manipulate them. So the idea of sinusoidal modeling is based on this observation that when we look at a sound, look at its spectrogram, in theory the spectrogram shows us where energy is at any time frequency location. So and we show that as the density of the pixel, the color of the pixel. That could be any distribution, right? I mean, you can't make any image you like on a spectrogram like this because there are constraints to do with the overlaps between the adjacent analysis windows. But pretty much, there are not very many constraints. We could have any kind of pattern of energy here, and that would be a real sound. Instead, what we see with many of the sounds that we care about are these kinds of patterns of ridges. And we know, and we notice that for this musical instrument, this is the violin, the bowed violin sound. So actually I can run this live. Right, so this is our little spectrogram running. And then oops, where is the sound file? With that sound file here, where is this? For some reason there's a buzz on the audio, so I'm muting it, but we see the harmonics coming through. This is, an A440 on the violin, and so we see there's this strong ridge at 440 hertz, and then again at 880, 1320, 1760, etc. And we understand these, we recognize these as the harmonics. It's not the only thing that's there. There's a little bit of background noise here. Some of that is actually just the coming from the spread, the side lobes of the analysis, because we're doing short-time analysis. Also, I noticed when I'm putting this together, there's some stuff in here which I think is actually alias terms. They look like these kind of ghost harmonics behind, but they're moving, whereas the main pitch has a little dip at the beginning. This thing has little peaks. I think it's a reflected down. And also, the frequency deviations are larger. But to first order, we see a bunch of harmonics. Now, if we zoom in on those harmonics, on those portions of the spectrogram, they're not infinitely sharp, right? They're blurry. They're blurry coming from the limitations of the time frequency resolution of our spectrogram. But at this level, they look kind of like stripes. And so that leads to the idea that we can simply describe this sound as a set of sinusoids, a set of parametrically described oscillators corresponding to each of these ridges. And if we could do that, then we'd end up with this very efficient representation rather than having to store, 512 frequency bins, complex values for every frame. We just have to store the parameters for each of these sinusoidal oscillators. And it looks like their parameters are relatively slowly varying, right? The frequency is relatively stationary, particularly for a musical note. So that makes it easier to represent, because then we can maybe subsample the representation. And we'd only have to store, 10 or 12 of them rather than hundreds of bins. And plus, the parameters that we'd store, which would be the frequencies and the darkness, the magnitudes of each of these points, has a very meaningful interpretation. It's like these are going to be the frequencies and magnitudes of sinusoidal oscillators, which then allow us to think about modifying those in with predictable results. So it's both an efficient and a flexible description. It sort of sounds simplistic. It sounds like one of those things that you could imagine doing but wouldn't work out in practice because, well, it's, the differences between your sort of cartoon interpretation of the spectrogram as a set of ridges and the reality of all this detail would be too large. And so when you did it, it wouldn't work. But it turns out that it does work. And it's pretty useful. So basically, the idea of sinusoidal modeling is to represent a locally periodic signal by its Fourier series. And so we have and so we're not requiring perfect periodicity, but just a signal such that when we take a Fourier analysis over some window, we get some fairly well-defined peaks. And then we'll approximate that signal as the sum of a set of sinusoids with some time-varying phase functions. We have a set of k sinusoids. Each of them has a phase function which varies with time, and an amplitude function which varies with time.
So n would be
N is the time index, yeah, like normal DFT. Now, if we're trying to represent a single time function, x of n, here we're representing it with k pairs of functions, alpha, a k and theta k. So we've actually ended up, using 2k times as much data to represent it. But the idea is that these things are smoothly varying, so we don't have to represent them with unique values at every sample point, but we can downsample, and then they become much less data than the original signal. Now here, again, if all the theta k's are unrelated, then we could, again, generate any sound. But often we're specifically interested in sounds with pitch, sounds with a specific, unique fundamental period, or fundamental frequency, omega 0, in which case we can just take the phase function and say, well, it's going to be some multiple times the fundamental at a particular time. And then to get a phase function, we have to multiply it by time, right? The frequency is the derivative of the phase. So the phase is I guess actually, for a time-varying omega 0, we want this to be the integral of the omega 0 through time. But for a constant omega 0, we can just multiply by time. And then, as with normal Fourier analysis or Fourier analysis synthesis, we can keep adding components. We can keep adding more and more of these harmonics and get successively more accurate representations. Where the signal is periodic or near periodic, we can add higher and higher harmonics here and get increasingly fine detail in the reproduction of the individual periods waveform. But even beyond that, if we just have other energy which isn't very well matched by a periodic signal, we can still think about just taking the Fourier transform of a single window and adding in individual little, we're just expanding it on a sinusoidal basis, and we can just keep adding terms to make it fit.
Would AK have its own defined equation too, or would it be specific to the harmonic?
No. So here, for a harmonic signal, we'd expect a relationship between all the frequencies. We expect them. We can sort of require them to be in fixed relations. But the AKs will be independent because that's what's defining the different instruments. Otherwise, we say that all these pitch sounds are the same and that they have the same pitch, but they're all distinct otherwise, and the AKs is what distinguishes them.
So would an instrument have, for example, estimate summation equation of an AK or something like that? Do you know what I'm...
So we've seen in the plucked string, we've seen that that can be generated with a fairly simple setup, and you could actually do an analytic treatment of that, and you could get expressions for what the initial AKs are, the energies of different harmonics, the Fourier series, and then how they decay with time, which is basically, in a simple system, they each have an exponential decay, but the exponential decay time depends on the frequency. And so you could, for a model like that, you could synthesize. You could have, closed form equations to generate the AKs. In general, we're doing this because we're talking about real-world instruments where there are a lot of effects influencing these things, and in general, they won't follow simple mathematical functions, and that's what gives them their rich, realistic character. But of course, you can create AKs however you want, which means this is another way of generating purely synthetic instruments from sounds from scratch by using mathematical functions to generate the AKs. In fact, the FM synthesis, which we spoke about a little bit last week, one of the ways of understanding that is that you are generating a set of sinusoids like this with amplitudes, but the amplitudes come from these Bessel functions, so the functions of the modulation depth. And the Bessel functions have a fairly complex set of, the different harmonics are generated by different Bessel functions. If you look at all Bessel functions for a given modulation index, they all co-vary in a complex way, and that's what gives FM sounds their interesting character, because with a single parameter, the modulation depth, you get all the harmonics changing in a different but related way. So that's the idea, that we're just going to take a spectrogram, we're going to look at the individual harmonics, and then try and drive sinusoidal oscillators from each of those. And so let's see how that works. And to see how it works, we're going to use this piece of software called Spear, which is was this package that was written by this guy, Michael Klingbeil, who was a student here in the Computer Music Center for a while. And so you can download this software, and even though it's been a few years since it's been updated, it still works great. So let's try that now. So basically, here's the window. You can read a sound file in. So let's go for that violin sound again. And then you get this panel here where you set the basically the parameter of the spectrogram that is going to use to pick out the tracks. So you set the basic frequency resolution, which is basically setting the length of the time window. And it chooses the window size and the FFT size from that. Has some thresholds for deciding what counts as a track.
How does the frequency resolution decide the time window?
So now it's 40 hertz, and it's giving me a window of 4,000 points, which at 44 kilohertz sampling is 100 milliseconds. If I wanted to have 20 hertz resolution, I want to have double the resolution, then I'd have to have twice as long a window, right? So now it's saying, okay, if you want 20 hertz, I need a 200 millisecond window here, because basically it's doing 4 times the period, right? So 20 hertz would be a 50 millisecond period, and it wants 200 milliseconds in order to be able to get that. So it just works that through. Basically, if you have if the window is too short, then you've got this, FFT giving you a set of frequency samples, and they're too far apart to be able to separately pick out the individual harmonics. Here we had basically a spacing of what they're calling frequency resolution of 40 hertz, And so, but we've got a fundamental of 440 hertz, so we've got 11 bins or something between each one, and we're in good shape. So this is what it shows us, and basically it's already done the spectrogram and the extraction of tracks, and so the actual representation, it looks kind of like a spectrogram, but now these are just individual contours. These are distinct contours. And so we can click on them to select them, and we can, we're actually picking up different parts of the energy. Now, we can play this sound, and even though it sounds like it sounds pretty good. It's actually resynthesizing that in real time. The buzz is not me. The buzz is somehow the screen is interfering with it. But what I can do now is I can select individual harmonics, and then if I press space, it plays everything. But if I press shift space here, it just plays the selected harmonics. So that's just the fundamental, and I can play the second harmonic, which is an octave higher as we expect. And then the third harmonic, 3 times F0, is an octave and a fifth, and then 2 octaves. Oops. Seventh harmonic, not an equal tempered note, and then the 8th harmonic. So you can hear there the pitches, the pitches of the individual sinusoids. They sound like whistles. They sound like individual sinusoids, and they all have different amplitudes, right, which we can detect. They have different amplitude variation, which is what's giving that violin its rich sound. We can select a whole set of them, and they fuse together to sound pretty much like a violin. If we take out the bottom ones, it still sounds like a violin, but it's kind of like it's become thin because we've removed the low frequency. It's like we're putting it through a high-pass filter.
Is this the effect you would have if you put your finger to the middle?
Yes, that's nice. So if you play a string, well, certainly if you play a plucked string instrument, then you've got the actual different oscillating modes on the string, and if you damp it in a particular point, then any harmonic that requires that can't be zero at that point will get taken out, while the other harmonics, a harmonic that has a node at that point will persist, and so you can knock out individual harmonics like this. If we select them like this, we're basically just like, it's like we're applying a bandpass filter. We're just keeping individual harmonics. But if we do something like this, where we select every other harmonic, now it turns out that this set of harmonics is now consistent with a fundamental here and the overtone. So we hear a note that's an octave higher, even though it's just it's in a sense just a filtered version of the original note, but with a very, very complex filter that knocks out every other harmonic. That sounds pretty convincing, doesn't it? If we take the complement of that, just the odd harmonics. See this one, the track got broken up in several pieces here. That has the same pitch and the same pitch variation as the violin, but now it sounds doesn't sound at all like a violin. You might say it sounds a bit more like a clarinet. One of the things about a wind instrument like the clarinet is that it tends to favor the odd harmonics, and so it's not completely true. It doesn't have even harmonics, but when you have a sound like that, it sounds more like a clarinet than like a stringed instrument. So this is doing the sinusoidal modeling, and the remarkable thing is that when we select them all, we do get a pretty convincing reproduction of the original sound. Now, you can see I set a threshold here of like minus 60 dB, 1,000th of the original amplitude, when I was building the tracks. And so you can see that there are, I guess, I don't know how well you can see it, but the color here is showing the energy of the track. And then, but sometimes there are these cases where there are tracks that sort of get interrupted, right? So this track here, it's clearly one harmonic, but here at this point the tracking sort of lost track, and so it resynthesized that as two parts of the gap. I don't know if we can hear the gap. It's kind of high up, but there is an audible gap in the resynthesis there. So we've seen one thing that this analysis allows us to do. It allows us to select individual harmonics, which is like applying a very complex time-varying filter. But given that all we're doing is now basically driving a set of... So one thing we can do with this is we can export the analysis like this, and this file let's see. This file is just a set of, it's a text file in this case, you know, with a set of setting up parameters, how many partials there are, partial count 74, frame count 549, how many time frames there are. And then basically for each time frame, it starts off with the time here. So it's basically, it's centering them on the analysis window, but this is, starts at 0.125, and then it's every 10 milliseconds, 0.135, 0.145. And it says how many harmonics there are. In this case, it's just one. How many sinusoids there are. The index of the sinusoid, its frequency, and its magnitude. And so the first two frames, there's just one harmonic at like 430 hertz. And then here we have 5 harmonics at 430, 855, 1742 with the different energies, right? So that's just the coordinates of these things. So here's, you see this, you can't really see it very well, but this apparently this harmonic starts a couple of frames before the other ones.
Where do you see the energy levels?
The energy is in this, it's in the color.
Yeah. Oh, so like, do you have a numerical number?
And in here, it's the second numbers after the frequency. So this is the amplitude, frequency and amplitude. And so we can read these into MATLAB. I have a oops. A function here, spear read, which just parses that text file format. Violin Arco FFA4. Arco FFA4. And so it just creates an array with the 549 time columns and the 74 frequency tracks. Has an array of their frequencies, array of their magnitudes, and the array of the actual time values. And so this you can do things like plot 3, which will do a three-dimensional plot of the frequencies and the magnitudes. You see that? But because when the track disappears, the magnitudes go to 0. So that's that's confusing that. So we'll do this thing of just saying that where f equals 0, we'll replace it with an NaN. And that makes those things appear much more cleanly. Oops. And so now you can see. So this is time along here this is frequency, and then this is magnitude in dB here. And so we're seeing, so if we look at this from straight above, this is basically this picture from Spear. We can also look at it side on to see the different magnitude plots. And we can similarly synthesize these. We can just drive these into sinusoidal oscillators in MATLAB to resynthesize from here. So once we've got these things which we're just driving for sinusoids, then we can talk about systematically changing their parameters. So now, here in Spear, I've got these different controls here. In particular, I've got speed and pitch. So this is the original violin sound. And then I can just make it move more quickly through the control points, or more slowly. Okay. And then I can do the same with the frequencies, because now to change the frequency, I just have to multiply each of these numbers by some constant factor. And so I can make it much lower. And so I can take the same analysis, but by scaling all the frequencies down. So if we look at what's happening on the spectrogram here, right, so when we play it at normal pitch, we see the harmonics coming out, but then when we scale it down, all harmonics are being moved down, and we're just multiplying the frequencies by a constant factor so that they still remain at constant multiples of each other. They just get moved down. And so here, this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, the 11th harmonic has this little break here. And now this little break shows up here because the 11th harmonic is the same track, and it's the same time base, but it's just this frequency has been scaled down. And so this is, this scaled down violin, it still has the same kind of temporal evolution, the same richness, right? It's got this natural sort of detail, but it's at a different pitch. And so this is now a very nice way of generating different versions, building a tune out of a single sample. So that's the illustration, and Michael Klingbeil's software is a very nice thing to do, but there are lots of different systems that do this. It's not that complicated in principle. It's just a question of detail to try and make it reasonably robust and reasonably flexible. So now I want to talk about a few of the kind of corollaries of this. So here's the typical kind of amplitude envelope we might get out. This is actually, you can see it's piecewise linear, but it's been interpolated to make it a smooth, a nice envelope I can use to drive my amplitude of my sinusoidal oscillator. And this is the kind of thing we typically get out. This is actually the fundamental of a violin, of a guitar pluck. So the guitar pluck sound is.
So that's the amplitude envelope?
Yes. Let me just play the original guitar with the muting off. Okay. And so this is now, I'm just taking the very lowest sinusoid from that and just resynthesizing that, and we get this. But the problem here is that basically I've got this long STFT spectrogram analysis window, and I need it to be relatively long to get the frequency resolution to pull apart different harmonics. And so, but what actually happened with that guitar sound was, the sound started at a very specific instant when the pluck release happened. And so there's this kind of softening of the envelope, which is not, which you could argue is not a particularly good representation. It's not, you know, the analysis window is going to pick up a little bit of this onset, even when it's sort of centered over here, and it's going to fade in. But really what happened was there was some particular moment in time where there was no sound and suddenly there was sound. And so you could argue that you want to have an actual envelope that goes like this. But this signal, if you listen to it, this one sounded like a little bit soft, like it was maybe being struck with a soft hammer or something, whereas this one has much more of a sharp click at the beginning. And you can see that in the spectrogram of the resynthesis here, where now we see this transient, which has broad frequency spread. You could never get this envelope out of a narrowband analysis because the envelope itself has too broad of a bandwidth to have come through a bandpass filter. But you might want to have this. So there's, this is the kind of a limitation that there's some signal which is most efficiently described this way, but it wouldn't come out of the sinusoidal tracking with those parameters. So sometimes people go back and try and look for situations like this and then truncate so that you have sharp onsets. Okay, so how do we go about actually making this analysis? What's going on inside the SPEAR software? And basically it really is just a question of looking at the spectrogram and looking for peaks and doing peak picking. And that's kind of like on the one hand, it's very easy. You just have a function and you look for local maxima. But on the other hand, it's kind of difficult to. It gets very fiddly, and to get it to work really well requires quite a lot of care. So we're looking at the spectrogram. The spectrogram is this short time Fourier transform. So we have a spectrogram as a function of the frequency index and the time window index, and it's just the time signal shifted by the time window index, some short time window, like a Han or a Hamming window, and then the Fourier transform here. This is a DFT, right? An endpoint Fourier transform. And so we're just going to look for, maybe at each time slice we're going to look for local maxima there. Now we know that this DFT is the samples of the DTFT, the continuous function of this particular continuous Fourier transform of this windowed time function, which means that its frequency spectrum is going to be the convolution in the frequency of the true underlying spectrum, the infinite time spectrum, and the transform of the window function. And this is kind of this gives us our blurring, right? This thing will have some main lobe width, and that blurring is what limits the frequency resolution. If this is too broad, then peaks that are close together in this will no longer be distinguishable. So we have to make sure that we're using a window that's long enough that we can distinguish the individual harmonics. It's long in time, meaning it's narrow in frequency. And this sort of makes sense that basically if we had some signal with some periodicity in it, and we're trying to recognize that periodicity in our Fourier analysis, then we need to see more than one cycle. Otherwise, this short time window, there's no evidence that it's going to repeat. The signal can't tell. So typically you have to use a time window which is at least a couple of pitch cycles long, maybe 2 or 3 pitch cycles long. Typically we're interested in, signals with fundamentals of a few hundred hertz. And so we need analysis windows of 50 to 100 milliseconds. We saw that the default setting for SPEAR was 100 milliseconds. But 100 milliseconds is it's a pretty long time that if we take the time structure of the signal and blur it out with 100 milliseconds, we can really hear that. And so it's, we're always having to play this trade-off between getting the frequency resolution we need and getting enough time detail that the sound still sounds naturalistic. Let me just show you that. Sorry about this hum. The buzz is really bothering me. But here's the original guitar sound, right? And it's pretty sharp. You know, it's a pretty sharp attack there. If we read it into Spear, let's just do this straight off with the default. Oop. Right, if you listen to the attack, the tone sounds right. It still sounds kind of like it's got the sort of resonance and the ringing, but the attack sounds very soft compared to that, where there's a definite, very clear pluck at the beginning. So if we do this again, but now use a much lower frequency resolution, still sounds pretty good, but now, right, the onset is much sharper because we're getting a shorter time window, so we're getting more of the temporal dynamics preserved.
Why could you do adaptive window?
An adaptive window, that'd be great, so that at the beginning you have a short window to capture the transient, and then as you sort of have these sustained harmonics, you have a longer window to give you better frequency resolution. Sometimes what you can do is you can have multiple simultaneous transforms, right? So you can have a short transform and a long transform running at the same time, and you can pick and choose between those, which gives you the same kind of thing. There was actually a report just last week of some work. I think it was done in New York at Rockefeller or somewhere, where they had been trying to investigate where the listeners can beat the time-frequency trade-off. That there's this, you know, the basic time-frequency trade-off is that the uncertainty in time times the uncertainty in frequency has to be larger than some minimum value. And so they were playing people two tones nearby in frequency, and then the second tone was also simultaneous with a marker tone remote in frequency. And then the listeners had to decide, is the test tone higher or lower than this one in frequency, and is it before or after this one in time? And so you're judging both the time and the frequency. And they showed that the listeners are able to do this. They're able to distinguish both time and frequency with a resolution that exceeds the theoretical constraints of the uncertainty principle. It's not like we're, you know, beating physics, because of course the assumption is if you know that there's just exactly one tone, you can do what you were saying, right? You could have one very long window which says, well, here's my peak, and then here's this other peak that comes up, and I can judge it. And then you can have a set of short windows that says, well, here are my onsets, and here's my other onsets. So as long as I know there's only one other tone in there, I can assume it's responsible for both the onset and the frequency. And so it seems like, yeah, the ear is able to do a trick, something like that. It's able to judge on the same, from a single instant, it's able to judge both the frequency and the timing. But of course, if it was a more complex pattern, it wouldn't be able to tell, because it's sort of lost the ability to correct. It's theoretically impossible to correctly assign those two together. But with a single event, you can do it. The problem of doing the adaptive thing would be, at the onset, you wouldn't necessarily have the frequency resolution to be able to tell the different harmonics apart. So, if you want to have these different harmonic tracks, how are you going to assign your frequencies to each harmonic? You could do it, right? But it wouldn't necessarily be exact. If you built a signal out of a set of harmonics with very rapid envelopes, you wouldn't necessarily be able to recover that. And it's kind of interesting that we see here on this short window the very, very beginnings, right? So now you can see the individual samples when we zoom in enough. Out here, it's got the frequencies pretty much done, but here are the onsets, and it's got this fairly narrow time window, so that when there's a rapid transient, it's kind of, I don't know, it's giving us some values here and it's not clear to me whether they really do correspond to physics or not. But of course, it's kind of a metaphysical question, because well, they do sum up to give you what you want, and so who's to say what the true frequencies of these harmonics should be? And so I'm seeing this sort of bend in here. That doesn't seem very likely. It seems like if you're plucking a string, you'd expect it to be a higher frequency at the beginning because it would be tenser. So I think that's just an artifact of how the spectrogram is calculated. This thing down here is a subharmonic, right? It's half the fundamental, and that's probably that's sort of some asymmetry between different cycles. That probably does have some physical reality to it. So this is basically what's going on inside there, that we have this kind of spectrogram thing, which we're calculating in the normal STFT way, and then we take an individual slice of this. We get a DFT slice, which at some point is a set of individual points, individual bins. Obviously, to make our job as easy as possible, we might oversample here, so that would mean taking a chunk of the window which was n points, but then using a longer transform, like 2n or 4n points, which would give you basically just interpolated values in the DFT. But we have a set of peaks here, so this is where we sort of see how what looks like a set of nice, well-defined ridges in the spectrogram is really just it's a continuous function in frequency, and there's not like ones and all zeros. There are a set of values, and in particular, because of there may be misalignment between the sampling that DFT is doing and exactly where the harmonics lie. Then we get a series of values, and typically the peak value will want to be between those bins somewhere. If we just take the single largest value, we're actually going to get fairly bad quantization effects. That, as we saw in SPEAR, the bin resolution was something like 20 hertz. But if the difference between an A440 and a semitone above it is only like 6%, so it's like 30 hertz, right? 20, 25, something like that. So that a 20 hertz resolution wouldn't even allow you to get a semitone particularly accurately at those kinds of frequencies. So you have to interpolate, but normally the interpolation is not that difficult, because we've got some kind of peak like this, and so we can take like the three nearest points and fit a parabola to them, and that'll give us an interpolated frequency and magnitude for the peak. This is kind of this is just like, oh, I've got some blurry peak, I'm trying to interpolate it, I can fit any function, and so it's sort of an arbitrary choice. But it turns out that what you're dealing with here is the convolution of some assumed line spectrum, a sinusoid, and the windowing function, w of e to the j omega. And if the windowing function was giving you an exact parabola, then this would be the right thing to do. With a Hanning window, what you get is not a parabola, but it's the sinc function. But if you use a Gaussian window, and it's a sinc function in linear magnitude, whereas actually I'm fitting this in a log magnitude. But if you use a Gaussian window, which is not that great a time window because it goes on forever, but you can truncate it and you get an approximation to a Gaussian time window, then the Fourier transform of a Gaussian window in time is a Gaussian window in frequency, and then a Gaussian in frequency, when you take its log, gives you this parabola. So it turns out that if you, with the right choice of time domain window, and then the right function fitting in the frequency domain, you can actually get something which gives you a pretty rigorous estimate of the true underlying frequency. Right, so far we've only talked about the frequency, but if you want to get a really, really accurate reconstruction, you can also try and estimate the phase of each of these frequency peaks, and you can then similarly interpolate the phase function of your DFT to get the phase corresponding to that particular sinusoid. once you've chosen where your peaks are, you can get their parameters pretty accurately by interpolation. But of course, the actual spectrum you're dealing with typically looks like this. There'll be some clear peaks, but then there'll be some other peaks which are not so clear. If you're using a finite length analysis window, which of course you always are, then you are going to get these side lobes, right? So if you get a strong harmonic, then out here there might be some little ripples which are really just the echoes, the farther out lobes of the effect of the time window. So you typically have to have some kind of threshold to choose which peaks you're going to keep. In an audio spectrum, very often there's a huge variation in amplitude between the high frequency and the low frequency. So you can't have a fixed threshold. So typically there'll be some kind of local threshold. So here the red line is a moving average of the dB spectrum here. And then the dotted line is that plus some, like a 10 dB threshold. And then we're only keeping the peaks that fall above this threshold relative to the local average, yeah.
So the small peaks are the result of aliasing?
The side lobe, some of them will be side lobes arising from the main peaks. I mean, you can call them aliases, but it's not the same as aliasing due to undersampling. But they are kind of they're shadows of a stronger peak. In this case, I don't think we're seeing those. I mean, this is clearly a harmonic signal, and so we've got the first four harmonics very strongly, but then, well, this fifth harmonic is there, but it's just below threshold, then 6th, 7th, 8th, and then 9th and 10th and 11th. So these are most likely true harmonics, but just there, but they're beginning to fall into the noise. So where does all this noise come from? You know, these other peaks and down here, some of that is just the combined effect of the spreading of all these local peaks, and some of it is just actual uncorrelated noise or aperiodic noise in the signal. So one thing you can do is you can just have a simple local threshold on a spectrum like this to choose the peaks. Other things you can do is actually you can look for stability through time. So if you do have a particular peak like this, it's like, is this really a sinusoid or is it just some spurious piece of noise? Well, if you look at the previous frame and there was also a peak here, then maybe you want to believe it more, whereas if there was nothing there in the previous or the succeeding frames, then it looks more like just a single bit of noise. And so actually in SPEAR, when we do the analysis, right, the two things it allows me to filter by are the amplitude threshold. That's actually an absolute threshold where I'll just throw away all tracks below some amplitude. But here's the amplitude threshold under peak, which is a local relative to the local peak. But I guess it's not in here. But in here, it allows me to select partials below duration. So if there's some track which lasts fewer than 0.1 seconds, like these tracks, then I can select them and then I can delete them, I think, to sort of clean up the analysis like that, right? Because that's often a big clue that it's not a very useful track. So then we've got, we have this set of frames. In each frame we can pick peaks, and then we're trying to form them into tracks. And that's basically the simple-minded approach of just trying to have a set of peaks and trying to see if they're the continuation of some existing track that you've got, and just gluing it on. That's basically what works. Now, the larger the step in here, the greater the chance that if the frequency is moving, it might end up being closer to the wrong peak. And so typically you want to use a fairly small time step here. And then as long as the frequency isn't moving too quickly, it'll be relatively unambiguous as to how to attach those tracks. And you'll have to have some process whereby if there is no continuation, then you mark a track as terminated. And if there's some new peak which doesn't have any preceding track to attach it to, then you instantiate a new peak. Again, those things rely on thresholds and they can be fairly sensitive, but typically you you can tune them to make them work. You can have some hysteresis so that if there is the threshold for eliminating a track is, threshold for whether you include this peak is lower if there's this preceding track than it would be if it were an entirely new track that you were trying to create. So with that process, you can get any set of harmonics, right? Any set of sinusoids from a spectrogram. It's just looking at spectrograms, trying to identify some kind of ridges, and then parameterizing each of those. So for a given sound, you might get a set of tracks like this coming out. But you sort of believe that this sound is coming from a harmonic source because it looks like these tracks are all harmonically related. So then you can sort of check that by dividing them by their index number, right? So if you can somehow recognize that they are close to being the multiples of the fundamental, you can divide them by that multiple, by that integer, and then plot them on a single plot like this, which shows the estimated fundamentals of all these tracks. This is real data. And what's interesting here is that, well, there's a cluster here where they're clearly all following the same frequency, but they're not. But there's some noise in each estimation. In particular, in the pink one here, which was a weak harmonic, we see there's a lot of uncertainty and noise. And also, for some reason, the fundamental here is consistently overestimated. And that could be something that I did wrong with the analysis, or it could be something about the acoustics, that for some reason that this is actually a clarinet sound, and that the, remember when we saw when we pushed the low-pass filter in the Carper-Strong feedback, we got a slight shift in pitch. It could be that the reflection at the end of the tube has a phase shift at the lowest frequency, which is actually changing the pitch slightly. I haven't ever seen that described in relation to the clarinet, though. Yeah.
So are these two different sounds?
No, same sound, but here I'm plotting the frequency of the harmonics, the actual frequencies, and here I divided each track, so they're the same colors, but I divide the track by 1, 2, 3, 4, 5, 6, so that now I get the actual fundamental. So if this frequency up here is meant to be 8 times this one, then here it is 1/8, and this is the actual frequency where it ought to fall. So now you can see here, this frequency around 600 hertz. There's a little lift at the end, but here, because now I'm only plotting between 550 and 700 hertz, this lift is this big jump up here. So this gives you an opportunity to improve your analysis. If you assume that you're going to have them be multiples of fundamental, then you can estimate the fundamental and just average it, and then assign them all keep them locked harmonically related. So once you've got the set of parameters, the frequencies and the magnitudes, then it's literally just driving it into a sine wave oscillator. You have a set of frequencies and amplitudes. You just multiply them point by point and drive them in. That's what I'm bothered again, because this should be an integral, not just a straight multiplication, but it kind of works, right? That you basically, as long as this thing is slowly varying, then the difference in phase between successive points is given by omega k. So this has been recognized as a viable way of synthesizing sounds for decades. It's just that actually calculating a sine function is, not that easy. Numerically, it's, you either have to do some kind of infinite sum or do some finite sum of terms, or you have to have a table look up with interpolation. And so typically, each sinusoid, each point would require many multiplies, like dozens of, 10 or 20 multiplies. And then to make a realistic sound, you might need 20 or 30 sinusoids. And so you'd be looking at hundreds of multiplies per sample. And at the time that, even in the 1980s when they were building FM synthesizers, that was simply not something you could do with a processor. Of course, today, as we've just seen with Spear, you can do that. That's fine. You can run dozens of sinusoidal oscillators at the same time. Although at some point you will run out of CPU power. Of course, we do know a quicker way to sum up a lot of sinusoids, which is to take an inverse DFT. The inverse DFT is essentially calculating the sum of all those sinusoids with particular amplitudes. And so if you can take your set of sinusoidal parameters and convert them into a set of DFT coefficients, you can use the DFT, the inverse DFT, the fast Fourier transform expression algorithm to resynthesize quickly. But that does require some, you can generate a lot of sinusoids, but they have to be on this fixed grid that the DFT is allowing you. So I'd have to use very long windows to get a very fine grid, or you have to do some kind of adjustment of overlapping windows to get intermediate frequencies. But once you've got this system going, where you've got the individual times and frequencies, you can do all kinds of modifications. As we saw, you can systematically scale all the frequencies by a fixed amount to change the pitch. You can stretch out the time points to get time variation. And of course, you can do this dynamically as well. So you can actually have something like this, where maybe you keep the time samples at their original rate at the onset, but then you stretch them out to sort of extend the sustained portion of the sound, and then maybe run them out at the same time at the end. And so you can vary the duration of a sound, which of course is another thing you might want to do if you want to have something that's under keyboard control. There are some issues in how you do the frequency stretching. If you have a sound which is like a voice, which is a periodic signal going through a set of resonators, if you stretch the harmonics, you stretch the pitch, but you also stretch the frequencies of the resonant peaks, right? So these harmonics are picking out resonant peaks. And that can sound unnatural because we're sensitive to the frequencies of those peaks. If instead you sort of try and sketch out the envelope, the frequency envelope that the harmonics are tracing out, and then divide that out, you can't really... on here, there's like the same trace here. You can imagine moving the harmonics, but then reimposing the same interpolated envelope to keep the sort of same broad frequency structure without... but while still changing the underlying pitch. So there are various, particularly voice analysis systems that try and do this, that will first pull out the sort of the general shape of the spectrum to get the resonances, then model the fine spectrum as sinusoids so they can modify it and then recombine them afterwards. Yeah.
I wonder, when you talk about the frequency response, it seems to fall into some Gaussian shape. But I wonder if you generated it and refed it into the analysis engine, would you still get, like, is there like a good statistical theoretical explanation for the Gaussian shape, or is it like a mathematical thing that happens in the analysis?
The Gaussian isn't coming from a statistical effect. It's just the overlap between, sort of what the inner product between differently tuned sinusoids is. If you think about it in the Fourier transform domain, that if I have this sinusoid with this window on top of it, and then I try and calculate the inner product with this other sinusoid, then depending on their frequency relation, I'll get some amount of non-zero residual.
If you reanalyze this one,
Yeah.
based on perfect sinusoid, you'll still get something that resembles Gaussians.
So the interesting thing is that there's this nonlinear step, right? There's this peak picking, right? So that if I have some signal, which is, and I, put it through a spectrogram, I get this smooth surface, and I then try and pick the center of those peaks. I'll get some discrete value out, which sort of, it's like quantization. It's like I'm pushing it back. I'm removing some uncertainty there. And so if you take a signal, you analyze it, and then you resynthesize it with sinusoids, and then you analyze it again. if you do it right, you can get into a stable situation where you get the same signal coming through. Because of this, the blurring of the analysis window, I'm just thinking, like, what are the limitations going to be? You're going to lose some temporal detail, certainly from the original signal to the sinusoidal resynthesis. But I guess that if you looked at the amplitudes, they'll probably get smoother and smoother, right, every time you go through. But if you do it right, if the signal's well behaved, they'll be pretty smooth to begin with. So the differences will be small, and at some point they'll be flat. But there's a reasonable degree of reproducibility here. But it's not a perfect reconstruction system because of this, the information you throw away when you pick the peaks.
You can use it to identify right?
Sorry?
You can use this to identify if something is synthesized or real.
That's an interesting idea. Yes. Right. You can see if one way of testing whether a signal has come from a model is to fit the model to it and see if it fits really well. And it's like, well, that's evidence that it's come from this. I mean, this is an original sound. This is the resynthesis using my sinusoidal tracking system, and it has these telltale gaps, right? So this is where the sinusoid tracker has lost something and then it's picked it up again. And so that, if you see that, then that's strong evidence that what you're looking at is the output of some sinusoidal analysis synthesis system. So the last thing I want to talk about is the energy that doesn't fit with the sinusoid. So here is the blue is an original signal. And then I ran the sinusoid tracker on this, and I picked out these big peaks of sinusoids. And then I resynthesized these. And of course, when I resynthesize them and then reanalyze them, which is what I've shown in green here, I get the same process of the analysis window sitting on top of the sinusoids and blurring them out. So I still don't get lines. I get these same shaped peaks. But you can see in between, the sinusoids tend to have these deeper valleys because there really is no energy except for the sinusoids, compared to the original, which has this sort of noise floor in between, right? And up here, I didn't even track these peaks, so these are left over. So I can form this red line, which is the difference between the green line and the blue line. It's the residual when I take the original, do the sinusoidal resynthesis, and subtract it. You have to be very careful to make the resynthesis line up really well with the sinusoidal components in the original. So for these, I had to measure both the amplitude, the frequency, and the phase, and resynthesize respecting the phase. Even so, when I take the difference, I mean, this red line is shifted down by, I guess, 20 dB, but I'm only like 25 dB or so below the peak. This is just the error between the resynthesis and the original. But mostly, this thing ends up being pretty flat, and it's like the background noise that was left. You can then take this signal, this residual noise, which you can listen, it's an audio waveform, right? You can, if you get it right, you can listen to it. And you can then model that. And so one thing you can model it with is as a low order spectrum like this LPC.
So you would add the LPC to the sinusoids?
Yeah.
So
Yeah.
Why did the original is so high when they overlap? I mean,
This peak here.
Yeah.
Yeah, exactly. So this is saying, so I shifted this down by 20 dB, but if it were on the same scale, it would be up around here. So what that's saying is when I took the original signal, which had a sinusoid around here, I then estimated the parameters, resynthesized the sinusoid, and subtracted it out, there was still, I just didn't hit that sinusoid right on, right? There was still minus 20, minus 25 dB sinusoid left in there. And that's just because the process of estimating those parameters, I don't know why it's worse for this one, but it would just, they're not exact. There's some noise in that estimation, and that's the difference. I mean, it's not going to be negative infinity, right? You're not going to get it exactly the same. There's going to be some amount of there's going to be some noise left in the difference between those, even at a given sinusoid. And you sort of, I don't know, I mean,
But it seems that the original and the sinusoid overlap for that clip. But then
oh, they do, yeah. No, but this is just, that's a dB scale for you, right? That these things are very, very close, but they're not identical. Otherwise, it would be zero. You know, at this point, when I got it to this level of match, it sounded okay. And so I didn't worry about trying to push it down any further. I don't buy what I'm trying to sell you, which is that, oh, you can never get any better than that. I'm sure you could get better than that. And knowing what thinking now about what I did then, this was fairly loose. It wasn't exactly, I'm only taking into account a certain number of points around the peak rather than doing a best fit, taking the whole peak into account. And I'm not sure how well I accounted for the actual shape of the analysis window. But at this point, it sort of doesn't matter because we're at a point where the residual in the gaps between the sinusoids is comparable to the estimation error on the sinusoids.
What does LPC stand for?
Linear predictive coding. We'll talk about it next week. But it's basically fitting an all-pole model to that energy. So let me just play you this example. So this is the original guitar. And then this is the sinusoid-based resynthesis with the gaps in it. It sounds pretty good. It's a fairly short analysis window, so it's still a pretty rapid onset. But it does have these missing bits. But this is the residual, the difference between those two. So you can hear some of these harmonics coming in. What's interesting is this little noise at the beginning, which is sort of the non-periodic part, the friction energy that comes from the mixture. Let me just play you those again. And so this is actually, that's that little peak, right? The fundamental, that's the mismatch of that peak. But this part is the part that you hear, which is sort of the rubbing noise and the background noise, which is kind of a nice effect. One other thing, of course, is that we're sort of talking about these tracks as if we can just pick them out. But if you have sinusoids which are overlapping in frequency, so here you can imagine two sinusoids crossing like this. So these are just little sweeps from 1,000 to 1,200 hertz. This is what happens if I add the magnitudes of the STFTs, the two sinusoids. But if I add them together and take their STFT, this is what I get. And what's happening here is that as their frequencies get closer, they start having constructive and destructive interference. And so you see these little these ripples coming in. You can sort of hear them as well, right? I mean, you can hear it as beating. But it isn't. But the point is that the spectrogram domain is not just a simple superposition. You don't just get the mixture of these things together. And even if you did, there become points where finding ridges would be hard because the ridges begin to interfere. So the sinusoidal analysis works very well with single sources. But if you have mixtures, like this is the sinusoidal analysis of a full piece of music, suddenly it becomes much harder to pick out the tracks. And so you can't. It's not a really great. A lot of people try to do source separation with sinusoidal representations, but it becomes very difficult because you get a lot of effects like this, interference between the harmonics. Okay, so that's pretty much it. The basic idea is we see these ridges in spectrogram. We're trying to extract the signal to parametrically describe each of those ridges as sinusoids. The peak picking itself is pretty intuitive. I mean, you can get more or less sophisticated, but essentially you're just looking for local maxima and then connecting them through time. The nice things about sinusoidal representations is that they're very, very natural domains for modification, for stretching in time and frequency, and doing other kinds of things like trying to combine parameters from different signals together to make these novel sounds. And then, even though there are some sounds which the sinusoidal analysis doesn't work very well for, like aperiodic sounds, you can use this sinusoidal plus noise system to get a nice effect there.